hear me? All right. I think it's all right. Yeah. Okay, I think it works. So let me just make sure I can have a pointer. And just 1 second. All right. So I'm going to talk about validating universal machine learning interatomic potentials with some experimental data. So this is a joint work between myself, who is computational, and my experimental colleagues. So before we proceed, I have a question to you. How many of you heard about universal machine learning potentials before coming to this workshop? Please raise your hand. Okay, so quite many. And the next question, how many of you have used it? Okay, yeah, it's quite several. Yeah, so great. I would encourage, if anyone haven't yet tried, to try them. I think that they're very awesome. So then my introduction will be a little quick. So here I'm showing the time and length scales of atomistic modeling, and the very much appreciated density functional theory is like a very great tool, but you cannot use it for extended time and length scales. And it was recognized with a Nobel Prize in '98, and Nobel Prize in 2013 recognized development of multi-scale modeling. And in older days, you had a lot of force fields, very classical force fields like Lennard-Jones and Morse potential, which are not very accurate, but you still cannot live without them. And the development was that you could use your quantum chemistry code, which is very costly in a very small region of space, and use less accurate classical force field in a large region of space, is like important for modeling drug binding to a protein, for example. And very recently, we are all experiencing this nice development of machine learning methods, which essentially allow us to extend the accuracy of DFT in computing forces and energies to a much greater time and length scales, and this is really great. So, and even if you don't run large cells, you will be very happy to see how quick they can do a calculation. And also, for those of you who do materials modeling for discovery of new materials, that means that we can do much more materials to search. So our graph is getting 3D here. All right, so, and for those of you who are not familiar with machine learning interatomic potentials, the idea is that regularly you have atomic coordinates, you have your quantum chemistry code, you get forces and energies, and you're happy. You can proceed with properties or dynamics, but this is costly. And you want all these, but you don't want this gray box, so you want to substitute it with something. And that's where when machine learning interatomic potentials come in, and they are essentially a very great interpolator. So you learn on some structures, and like you learn on atomic coordinates and energies, forces, and that's a great interpolator. But normally, when you train MLIPs from scratch, you do this for, let's say, one compound or a couple of compounds or your system of interests. So it's a little bit like heavy to use them. And a very recent development in a couple of few years is, yeah, before we'll tell you about recent developments, I want to say about state-of-the-art MLIPs. So the question is how costly it is to use them. I think that's a very practical question. So I sampled state-of-the-art works that focus on kind of single-phase material. I want to stress out there is no defects, there are no interfaces or grain boundaries, so it's a very plain problem when you have just one phase and you just model that. And your question is how accurate you're in predicting forces and energies. And this is state-of-the-art with different architecture samples. So the bottom line that state-of-the-art error is kind of below 100 milli-electron volt per angstrom. That's kind of where you could say ab initio accuracy starts at this level. And the training dataset size is on the order of 500 structures. So this is what we have. This is state-of-the-art. Now, the recent development is that people has done training for practically the whole periodic table, training on large databases of inorganic materials where you have millions of DFT computations. And that's very great. Now you can call these universal machine learning potentials. So that's how terminology has evolved. And the idea is that you can use them practically out of box. So you take your compound, whatever it is, and you use it out of box and be happy. But still, you better tune it, perhaps the final output layer, so you can fine tune it for your particular compound. And this is what we're going to talk about. The question is, how expensive is this and how well does it work? So the development of this field is really rapid. This is actually quite outdated, and you still see quite many force fields here. We have chosen this crystal Hamiltonian graph neural network, or ChargeNet. One reason for that is that motivation that it supports computation of magnetic moments, and it learns on magnetic moments, which in my opinion is very beneficial. Thinking ahead, a lot of stuff we do in material science is transition metal oxides, like catalysis, batteries, cathodes, whatsoever. So you will have a mix of valences, so it's something to think about. And another benefit, in my opinion, is that number of model parameters is very low compared to the dataset size. And this, in my opinion, speaks to some sort of elegance and robustness of the architecture. So, all right, and, we're gonna see how it performs. So the question we ask here is how costly it is to fine-tune. So in essence, how many DFT snapshots I have to provide to this neural network so it learns and fine-tunes and is working very well. And another question is how valid it is, can I trust the benchmark? So what do we do here? We select a tungsten sulfide material. So we use progressively increasing size of the DFT dataset and see when it's enough to stop. And we benchmark against both DFT, which is like structure and forces, and we also benchmark against experimental data, which in this case is EXAFS, X-ray absorption spectroscopy, which is very sensitive to the structure and also very sensitive to vibration amplitudes, which makes it very suitable to test as a force field. In previous years, our group has done some validation of moment tensor potentials, but for much simpler systems like cubic metals. So here you can see that experimental spectra and theoretical spectra match pretty well, which signals to a very accurate performance. But here we would like to go to a little bit more complex structure, so from cubic crystals to sulfides, and here we have also some van der Waals gap, which adds some complexity. Also, I must tell that practically none of the existing umlips were trained on van der Waals interaction, so here we are kind of providing some extra kind of quest for the training. So this is a result of the fine-tuning. You see a parity slope of umlip force versus DFT force, and you see if you use umlip as it is, you have quite a large error and also quite an incorrect slope, which signals to this softening. So in other words, it means when your atom displays from equilibrium position, you underestimate the force and you underestimate the energy. So that's softening and it's not correct. And when you fine-tune the ChargeNet final layer on the 7,000 DFT structures, it's getting pretty much fixed. So it's very good. But the question is, of course, maybe 7,000 is an overkill. Maybe there is a middle ground. And that's what we're going to figure out. So here I'm showing the error in bond length, van der Waals gap, and also force error versus number of DFT frames. So that's how many structures I use. And you see pretty much that even with on the order of 100 structures, I get a quite accurate bond length. I get quite, well, not quite, but reasonable van der Waals gap. And also this error is getting comparable to state-of-the-art MLIPs, which in my opinion is very good. And of course, you can increase the number of data set to make it even better. So there's kind of a trade-off between how much you can invest and how accurate you need. Also, in the literature, it was suggested to use much less data points, like 1 to 10. So we have tested that, and we see that it doesn't work very well. Particularly here on 10 structures, we see that van der Waals gap is quite off. Perhaps the reason is that that umlips were not trained on van der Waals interactions, and for that reason, you better provide a little more data to train it. All right, so now we turn to EXAFS. So EXAFS stands for Extended X-ray Absorption Fine Structure. So when you have when you vary energy of your X-ray and you see how absorption change, you have this absorption age when particular element starts to absorb X-ray, and also you see the subtle oscillations in energy. So that's what is EXAFS. And the formula is telling us that it is very sensitive to structure and in a very complex manner. And you have to sum over all of the paths of the scattering. So each atom has about 1,000 scattering paths within the kind of mean free path of that photoelectron excited. But the good idea is that, so essentially it's sensitive to amplitudes. So at every temperature, you will have a different EXAFS spectra because amplitudes are temperature sensitive. So the good idea that we can do MD calculation at a particular temperature that is consistent with experimental measurement, and we can see and compare how good it compares. So all we need is a molecular dynamic simulation, and then we use multiple scattering theory to compute the spectra. So we do see in this result, here is experimental EXAFS spectra versus the wave number. We do see a softening, and I will show you where exactly. So you see that vanilla ChargeNet, which was not tuned, is a red line, and it kind of, the damping is much stronger here than as an experimental signal. And once you tune it, the blue line fits perfectly the experimental data, which is very good. You can also see the same in the Fourier transform. So here is an underestimation of the Fourier transform by untrained, like untuned ChargeNet. And once you tune it, you get it much, much better. But again, the question is here about the middle ground. So do we need, how many structures do we need? And so we tracked how the error in EXAFS analysis changed with a number of frames. So you see that, well, if you use one or two structures, if you're on a very low budget, then one or two structures will help you. That's good. But if you want to get to a very good result, then probably you need like on the order of 100 structures to decrease this error in EXAFS. So error in EXAFS is practically like agreement between this experimental signal here and your model signal. And also we see that it aligns with the error in forces. So we also see that it goes in hand with decreasing errors in forces. I must say that this error does not go to zero, and perhaps for a good reason, because when we use force field, we train it to particular DFT functional, so we cannot get better than DFT functional. So there is some potentially room for improvement. Also, of course, we always have some systematic errors in experimental measurements and systematic errors in like multiple scattering theory. So we shouldn't perhaps expect that this error will vanish, but maybe someday. So maybe we can manage with another exchange correlation functional to get it even lower. Yeah, so the final here suggestion is that we can use on the order of 100 structures to make it work. And I'm come to conclusions. So these 100 structure recommendations that we see from our data is kind of more appealing than using MLIPs from scratch. So state-of-the-art MLIPs would require you a little more structure, supposedly. We also see that ChargeNet effectively learns on van der Waals interactions, which is very good in my opinion, because it was not trained on. And yes, this double benchmark on DFT and EXAFS provide us with some extra reassurance on capacity of the MLIPs. And yeah, so thank you. I would like to acknowledge the funding agencies and thank you for your attention.
Thank you so much, Peter, for that wonderful talk. Do we have any questions?
Great talk. It's really interesting. So you showed that when you fine-tuned on PBE plus D3 data, you learned the van der Waals correction. But did you explore just adding the D3 correction directly to ChargeNet?
So I haven't. Yeah, that's a great question. So I haven't. I believe it would require less interactions to do that. So that's expectation. So I haven't because like at the time it was not implemented there. But of course it's not. It's not implemented yet either. It wouldn't be a big deal for like if I would be stubborn on this. But also I was thinking that, okay, so this D3, yeah, nowadays you can compute D3, but let's say I would do some more complex van der Waals function like RPA or, I don't know, maybe some other correction of van der Waals. So this would give me an idea how much I would have to invest.
Any further questions? I'm seeing no hands, but that's most likely because we're all a little bit peckish and in need of caffeine. Oh, yes. Okay. Thank you, Milica. It has come to my attention that today is the last day of the conference. I'm sure to the great dismay of everyone here. If your travel was funded through the Demon Cost Action, we kindly request that once again you sign in today with our little pamphlet. They'll be at the front desk. If you don't sign, apparently there are some financial consequences that perhaps you will be surprised by. But okay, so please do that during your coffee break. Please enjoy the refreshments. We will reconvene here for our final session. Sort of sad to say that. At 11. And for those of you who are interested in ringing the gong as a way of signaling the end of the coffee break, do come a little bit before 11 and you can